Hi, everybody. This is a presentation about the topic of calorimetry. What we're going to do in this presentation is define calorimetry and several of the other vocabulary words that go along with it. Kind of recall the different, what's the difference between heat and temperature, and then also learn how to do calorimetry calculations where we can either calculate the heat transfer, the temperature change, or the mass during any calorimetry process. So what is calorimetry? Well, it's a process that's used to measure the amount of heat that's released or absorbed during some sort of change, like a physical or a chemical change. So in here, inside of this little container, get a different color. Inside of here, I don't know if you could see that's at O2. This container right here is where you would put some sort of sample that through this external ignition unit, they would start combustion, okay? And when that little sample, whatever it is, undergoes combustion or the change process begins, if it gives off heat, it's going to, the heat's going to pass from this little combustion chamber right here into the water that surrounds it. If heat travels into the water, that's going to make the temperature go up, and you can measure how much the temperature goes up. You can also measure how much water you put in here. And I'm going to show you today how you know, if you know the amount of water and how much the temperature goes up, then you can figure out how much heat was absorbed by the water. This area around the outside, this, what they're calling the dewar, a dewar flask or a dewar container is just one that has like an air or an insulating type of layer. And then this is kind of insulating top too, so that any heat that is given off by the, change that's happening in here, goes into the water and doesn't, like, it prevents it from passing off into, the surroundings. Usually there's some sort of stirring device too to like keep the heat spread out evenly. And if heat's absorbed, then the opposite happens. The temperature will go down. And then when the temperature goes down, as long as you know how much water, you can figure out how much heat was absorbed, because then the heat traveled into the, the change. And you can figure out how much heat was lost by the water. So then you know how much was absorbed during the change. So let's get started on some of the definitions. We know we've had this in the past, that heat is a form of energy that can pass from warmer to cooler objects. Okay. And heat, remember, we talked about this earlier, is the total kinetic energy of, of a sample. Okay. All the particles and their motion, is the heat. Whereas temperature is the average kinetic energy of a sample. So I could have two beakers that are both at, they could both be at room temperature. If this one has 100 milliliters of water and this one only has 10 milliliters of water, if they're both at room temperature, like 25 degrees Celsius, they have the same average kinetic energy. They have the same temperature, but this beaker right here has more heat because there's more particles in that beaker. There's more total kinetic energy due to the larger number of particles. Okay, so hopefully that differentiation makes sense. Now, calorie is a unit of heat, okay, and it is the amount of heat that's needed to raise the temperature of 1 gram of water by 1 degree Celsius. So each gram of water that changes 1 degree Celsius, that's a calorie of heat that's going into the water. If you have a gram of water and it goes down by 1 degree Celsius, then that's just heat that's lost, but it's also still a calorie. Then you lost 1 small c calorie of heat. The small c part is important. You'll see why in a minute. And one thing I wanted to note here is that This works in your calculations whether you start at like 20 and go to 21, or whether you start at 30 and go to 31. Each degree Celsius that the temperature of the water goes up requires a calorie for every gram of the water. Okay. Calorie is the English unit of heat. To put it into the SI or the metric unit of heat, here's a conversion that's going to be very handy for you to know that a calorie is the same as 4.184 joules. Now, how you're going to do these calculations, okay? Water, since it was used to define a calorie, has a specific heat of 1 calorie for every gram degree Celsius. So let's say I have like 200 grams of water inside of this container right here, okay? And let's say that when the temperature goes up, okay, as heat travels from the reaction out to the water, let's say that the temperature went up 10 degrees, okay? So the temperature goes up by 10 degrees Celsius. So we know that for every gram and every degree Celsius, we need a calorie. If you even just look at the units, you can usually just see what to do with things. So if we take the mass and we multiply by how much the temperature went up, and we multiply by that specific heat, 1 calorie per gram degree Celsius, we can see that our grams divide out, our Celsius divides out, and we would be left with how many calories of heat. So 200 times 10 times 1, this would take 2,000 small c calories of heat to get the 200 grams of water that's in this area to go up by 10 degrees. So if we conduct this change in here, and this is what happens, this is how much water and how much temperature went up, we know that this change gave off 2,000 calories of heat. So that's kind of how the calculations work. Some other handy conversions before we take a look at the equation. Okay, we already had this one. We know that a calorie is 4.184 joules. 1,000 joules is the same as a kilojoule, just like 1,000 meters is a kilometer. 1,000 calories is a kilocalorie, but this is where instead of saying kilocalories, they will often just say, oops, I'm in the dark, sorry. They will often just say the word calorie still, but now spell it with a capital C. So a capital C calorie is really a kilocalorie. So a capital C calorie is 1,000 of the little c calories, okay? So a capital C calorie is enough to make 100 grams of water go up 10 degrees. Do you see that? Now, why this is important, you check some food labels. If you have, for example, like a Snickers bar and it says it's 350 calories, I guarantee you it's going to be starting with a capital C. Because when we say like, oh, he's on a 2,000 calorie a day diet, we're talking about the capital C's. We're talking about 2,000 and then times another 1,000 to make it the small c calories. So that's really what, like 2 million small c calories to be able to, apply to water and make the temperature go up. So anyway, just wanted you to note that when we talk about a calorie that's a small c, it takes 1,000 of those to be 1 calorie in your food, okay? So your food's giving you a lot of energy. So specific heat capacity is the amount of heat that's needed to raise the temperature of 1 gram of a given substance by 1 degree Celsius. Now, we know that for water, that's 1 calorie because water was used to define a calorie. So for water, the specific heat capacity is 4.184 joules for every gram degree Celsius because, that's 4.184 joules is the same as a calorie. Notice here's some other substances. Okay, you can't see the zinc is under there, 0.387 joules per gram Celsius. But do you notice that the metals have really small numbers? It doesn't take a lot of heat to make a gram of metal change temperature. And we know that. We know that metals heat up and cool down really quickly. If you lay something out that's made of metal on your sidewalk, like a metal pan, and the sun hits it, you might go to touch it and it's hot. You have some coins laying out in the sun, you go to touch them, they are hot. That's because the specific heat capacity is pretty low. It doesn't take a lot of heat to get a gram to go up a degree. Now, water, we know that it takes a while to get the water to heat up, right? Like a pool. This is why it takes a pool so long to heat up at the beginning of summer. It's a lot of grams of water. And every single gram takes this many joules to go up just 1 degree Celsius. So, water can absorb a lot of heat without having a really huge temperature change. So that's why water is good at cooling things. It can absorb a lot of the heat, okay? And the only reason we don't use it in cars is because our cars get too hot. The water would boil off, it would evaporate. So instead we use antifreeze, which is pretty good too. Look, it can absorb a good amount of heat. And so that's why we use that. It doesn't evaporate quite as easily. So anyway, there's some numbers. These are numbers that maybe you want to take down because you're going to be using them in some problems. I know it's a little tough to see the zinc under there. Oops. And the one that's listed under there, zinc's specific heat capacity is 0.387 joules for every gram degree Celsius. And if you look these up on the internet, sometimes you find slightly different versions. Now, one thing you want to be careful of when you look them up on the internet and you see a slightly different number is that it could be expressed in different units. But even if it is expressed in joules per gram degree Celsius, sometimes there's slightly different numbers reported by different labs and depending who measured it. So here's the equation. So if we know the mass, which is the grams, and we know the temperature change, which is the degrees Celsius, and we know the specific heat, which is, depends on the material, but that's the number of joules for every gram degrees Celsius, then we can easily see how the grams and the degrees Celsius will cancel and we'll be left with joules, which is the heat gained or the heat lost. Now, if the temperature goes up, okay, we get a positive answer. That's because heat was gained by the water if its temperature went up. But, if the temperature goes down, right, like if temperature goes down, then we get a negative answer. That's because heat was lost. And so you need that negative on the answer. That means that the system, like the water, lost some heat. So you do have to pay attention to units. As long as this is in joules per gram degrees Celsius, you can use your mass in grams and your temperature in degrees Celsius, your temperature change in degrees Celsius. But you do have to watch. Occasionally the masses will be in a different unit, and then you have to make sure that your mass unit matches up. To get the temperature change, you take the final minus the initial temperature. So if something went from 10 up to 20, that's a change of positive 10. But, if it started at 20 and it went down to 10, that's a change of negative 10, and you're going to get a negative heat change. And again, you could put temperature in other units, but it has to match up to whatever unit is being used in the specific heat. So again, make sure you're matching up your temperature units. And the specific heat capacity, remember, that's specific to the, if it's gold, you got to use the specific heat capacity of gold. If it's water that's changing temperature, you got to use the specific heat capacity of water. So you need to use the number that is specific to whatever material you're using. So let's solve. I just have 3 problems to solve together. We always, in all of these, want to use this equation. Okay. I think it's a really good idea, since we're getting a lot of variables, to kind of list what we know. So the delta Q, we don't know that. That's what we're trying to find. How much heat? Okay. The mass is 178 grams. The temperature change, remember, you take final minus initial. And I'm going to follow our sig figs. That's 5.0 degrees Celsius. And then the specific heat of water is 4.184, and that joule is joules per gram degrees Celsius. So one of the reasons I like to list everything out, first of all, I want to end up with only one variable that I'm still looking for. And also, I like to see if my units match up. Like, for example, if this said 2.0 kilograms of water, at this point, I know I need to do a conversion of the mass so that the units match up to the units I have for specific heat. Then I like to do my algebra, okay? So I'm trying to solve for the Q. I don't really need to do any algebra. That one's already solved for. So I'm good in this one. And I can just start plugging in numbers. There's my mass. Change of temperature, it went up 5 degrees Celsius, and it is 4.184 joules per gram degrees Celsius. And then, oops, I need a lighter one. And then I need to get rid of the units. The grams will divide out, the Celsius divides out. And when I multiply here, I am initially going to get 37.24. I get some other decimal places, but because of the 5.0, I need to round this to 2 sig figs. So I'm going to make it 30. I'm going to make it 3,700. Okay. And that's going to be joules. Or if I want to put it into sig fig, or not sig fig, scientific notation, I could do 3.7 times 10 to the third joules. I could also be asked to put this in other units, like kilojoules, in which case I would need to do a little conversion. There's 1,000 joules in a kilojoule, and then I would get 3.7 kilojoules. So you got to be careful when you're doing your problems. Kind of look at the units very carefully. Do they want it in joules? You could give either one of these. Do they want it in kilojoules, or do they want it in calories? In that case, you could have used the specific heat of water in calories, but some of the other ones, we don't know it in calories. So if you get an answer in joules, you'd have to convert to calories. So you really got to pay attention to your units. Let's try another one. So again, I'm going to use my equation that, we have. So I'm going to kind of list what I know. I know that I have 4.250 times 10 to the fourth calories of heat. Mass is what I don't know. How many grams? I'm looking for that. The change in temperature goes from 25 up to 35.5. So you always take final minus initial. So it's going to go up 10.5 degrees Celsius. And the specific heat capacity for gold, if you go back a couple of slides, is 0.126. And that is joules per gram degrees Celsius. So I don't know if you can see it here, but I've got a little conflict of units. My heat is in calories and my specific heat is in joules. So I better do a little conversion. 4.250 times 10 to the fourth calories. I know that there's 4.184 joules for every calorie. So I need to do a little conversion there, and I get, instead of the answer up here, the heat in calories, I'm going to put it in joules. I get 1.778. I'm going to keep at least the 4 sig figs that I already had, times 10 to the fifth joules. And that's the number that I want to use in my equation to make sure that the units divide out. Now I'm trying to solve for the mass here. See, this is my unknown, right? So I got to do a little algebra. I got to divide both sides by delta T and C, because the mass is going to be equal to the change in heat over the change in temperature times the specific heat. You see how these dropped out? So now I'm just going to make a little room for myself here. So now if I am calculating the mass, I put the heat, 1.778 times 10 to the 5th joules. Oh, I didn't mean for it to be that long. Sometimes I get the most random stuff on here. It's really touchy. And then on the bottom, I'm going to put my temperature change. And I'm going to put my specific heat. Okay. Now let's examine these units carefully. The joules will divide out, and the degrees Celsius will divide out. And I'm left with, for my units, 1 over grams. This is just the same as if you had, I'm going up here in the corner. I don't know if you see me up here. 1 over 1/2. If you simplified that, you would invert and multiply and get 2. You would invert the bottom fraction and multiply. So same thing here. This is the same as grams. So our unit on our answer is going to be grams. Okay. To solve this, you divide by both of the numbers that are on the bottom. Either that, or you need to, when you're plugging it in your calculator, put like a brackets around that. So I'm going to plug in that the joules. I'm going to divide by 10.5. I'm going to divide by 0.126. And I got, with 3 sig figs, 1.34 times 10 to the 5th grams. Okay, that's a lot of gold. Okay. So another problem that you might be asked to do might look like this. So again, we're going to use the same equation. And a lot of times I get students think when they're listing out, okay, what do we know? All right, now this one loses 78 calories of heat, so we need a negative there. Okay, it loses that many calories. And I'll get a lot of students who'll say, you know what? I don't have a variable, Mrs. Gladfelder, because they will do this. And do you see what's wrong with that? I'm just going to try and get rid of my random line there, which also gets rid of my 2. Okay, do you see what's wrong with this right here? Because it's wrong. That's just the initial, right? That's the initial temperature. That's not the change in temperature. So we don't know change in temperature. All we know, and you know, sometimes I like to make a note of that, but the temperature initial, okay, is what? 48.7 degrees Celsius, but we don't know the change. All we know is that the change of temperature is equal to the final minus the initial, right? And then since it's water, you can use the specific heat of water in calories, or we know that it's 4.184 joules. Since this is in calories, I'm just going to use it in calories. Whoops. My brain's getting ahead of my pen's getting ahead of my brain. I'm going to use it in calories per gram degrees Celsius because then my units match up. So what I need to do here, okay, is I need to split that delta T into T final minus T initial. So this is really delta Q, change in Q, is equal to M T final minus T initial, and then times C. Now, if I am solving for the final temperature, first I'm going to divide both sides by M and C. So delta Q over MC is equal to the final minus the initial temperature. And then, do you guys see, I can just add the initial temperature to both sides. Over here, it'll divide out. So T final, I'm going to put my equation down here, and then I'm going to erase some other stuff. T final is going to be equal to the delta Q divided by MC, And then we're going to add to that the initial temperature. So we've really used our algebra, haven't we? Because we're trying to find this. So we divided both sides by M and C, and then we added the initial to both sides. So I'm going to make some room for myself now. Okay. I just have a piece of paper. I just keep on going, but it comes out of room. So now I'm going to go back, and to get the final temperature, I need the Q, negative 78 calories, divided by the M, 25 grams, and also divided by the C, 1 calorie per gram degrees Celsius. And then I'm going to add to that 48.7 degrees Celsius. Now over here, the calories will divide out. Calories divided by calories, that's going to divide out. And this is grams divided by grams. And I'm left with this 1 and then 1 over Celsius on the bottom. So this one's going to be Celsius when I solve this. So I'm going to take negative 78 and I'm going to divide by 25 and divide by 1. And I got negative 3.1. Oh, the 78 was 0.0. I was just going to say, I thought I had 3.6. Minus 3.12 degrees Celsius. I have to add to that 48.7 degrees Celsius, and those two give me the final temperature. Now, when I add them, look, I only know this one to the 10th. So I can only keep my answer to the 10th. And when I add them together and keep my answer to the 10th, that's what I get. So that would be the new temperature. Now that's lower than where you started, but that makes sense because if it loses heat, the temperature of the water should drop. Okay. So hopefully doing a couple sample problems, and you can certainly stop and copy down or go back through and try them again. But hopefully you see how to solve the calorimetry problems, because that's certainly going to be our biggest challenge is math, where calorimetry is the process. Calorimeter is the piece of equipment where you conduct the change, and heat is either transferred to the water or absorbed from the water, and the temperature of the water will go up and down. And then these are all just units, okay? And then there's kilojoule as well. And then specific heat capacity is the C value. It's unique for every substance. And I think we can see the difference between heat. That was the total. That's the delta Q, because that depends on how many particles, the mass. And then the temperature is the average kinetic energy. Okay? So good luck, and see me with any questions. Thanks for joining me.